Hello everyone. Welcome to the talk of multimodal large language model. I'm Guanyu Huang from University of Sheffield. Today, I'm going to host the talk of Haiyan Zhao from New Jersey Institute of Technology. Today's talk, it is the sixth talk of multimodal large language model. You may have attended our previous talks. If it is your first time here, like me, let me briefly introduce what talk on MLLM is. So the first keyword is multimodal, which enriches the use and the development of large language model in combination of other modalities, such as text, image, audio, and video. In addition, MLLM is a multidisciplinary field, which goes beyond text generation. For example, it is applied in finance, law, and image generation areas. It also provides multi-perspectives to study social behaviors. So, talk on MLLM started on 1st July 2023. There were 5 talks in the past few months, covering various aspects of multimodal large language models. At today's talk, we have Haiyan Zhao with us. Just a sec. Oh, yeah. So, at today's talk, we have Haiyan Zhao with us. Haiyan graduated from Huazhong University of Science and Technology with an award of Outstanding Graduate in her master program in 2019. She is now a first-year graduate student in the Department of Computer Science, New Jersey Institute of Technology. Currently, she is working closely with Professor Mengnan Du on model interpretability. Her research interest lies in explainable AI. Today, Haiyan is going to talk about her work on explainability for large language models. The talk will be recorded and shared in our group WeChat. If you have any questions, please feel free to leave them in the chat. We will discuss them in the question and answer session after the talk. Of course, you can also unmute yourself in the Q&A session. So now, without further ado, I will give the floor to Haiyan.
Good evening, everyone. Thanks for introducing. And today I'm going to talk about explainability in large language models. And this talk will consist of 4 parts. At first, I will introduce some background of large language models, and then I will introduce explainability techniques, which will be divided into 2 parts. The first one is the traditional fine-tuning based paradigm, and the second part is prompting based paradigm. And then I will share some ideas about the future research. The explainability techniques here I'm going to introduce is mainly based on our survey, which has been posted a few months ago on Archive and GitHub. And if you are interested in, welcome to read and inspire. Natural language processing has been widely applied into multiple tasks nowadays. For example, it is applied in chatbots, question answering, text summarization, and code generation. I think this one would be widely used by us when we write code. We can use Copilot. And some other downstream tasks. There are mainly 4 paradigms in natural language processing. The first 2 are mainly supervised learning based, which is a little bit outdated because they are mainly targeting at the small data set. And the second 2 paradigms are what we are going to talk about today. The first one is fine-tuning based, and the second one is prompting based. For traditional fine-tuning based paradigm, it's mainly composed of two steps. The first step is to pre-train a base model on a large corpus of textual data. And then we can fine-tune this base model on a set of task-specific labeled data. For example, if we want to fine-tune this base model into the medical areas, we can use some medical-specific labeled data to fine-tune this model. And the representative models include BERT, Robota, and Electron, and so on. For prompting-based paradigm, it also include two steps, and the first step is the same as the traditional based ones, but the second step is very different. It doesn't need a domain-specific dataset. It usually uses the instruction fine-tuning dataset, which consists of question and response pairs. Because for prompting-based paradigm, it has a feature learning ability, and which I will introduce about what is feature learning. And there are some representative models too, which include GPT-3 and above, and Llama and Claude. Actually, the development from traditional based paradigm to prompting based paradigm is basically a scaling war, and this war happened in 3 dimensions. The first is parameters. As we can see from the graph, in the last 5 years, the parameters grows from millions to trillions. Of course, with more parameters, we need more data to train the model, and the aggressive growing of parameters and data makes the computation grow aggressively too. So after we developed large language models and invest so much computation resources and time to train this model, what we get here are 2 very important abilities for large language models. The first ability is its feature learning, and the second ability is chain of thought prompting. Before that, I want to introduce what is feature learning. That means when you give the model a few examples, it can learn from these examples and make inference. For example, here we give the model a description of the task. We ask the model to translate English to French, even if it haven't seen this, and we then give it 3 examples. It can learn from this inference pattern. For example, we give it the chase English word, it can give you the French version. And this kind of inference doesn't need fine-tuning. And the second ability is very important too. It is chain of thought prompting. Actually, this kind of ability enables large language models to have reasoning abilities. For example, in the standard prompting, we usually give it the question and the response pairs, and this response are mainly the direct answers to the question. For example, in the left part of the figure, we can see that we ask the model that if Roger have 5 tennis balls and he buys 2 more cans of tennis balls, each can has 3 tennis balls, then how many tennis balls he has right now? We give the model that the answer is 11 directly, and then we ask the same questions to make the model to answer it. Usually it will fail because such kind of reasoning tasks involves multiple steps of reasoning steps. So without the thought process, or without the explanation that we give it, the model can hardly make the reasoning itself. So we can change the example we gave the models. We can see in the right part of the graph that in the answers we instead of giving the model the answer directly, we add a sentence to explain how this answer is get. Or C, we give the model that the thought process of human beings. We can see here that we tell the model we can compute the 2 cans of 3 tennis balls first, that we get 6, and Roger still has 5, so the final answer is 11. And then we give the same question to the model again. With this chain of thought prompting, the model is able to mimic the reasoning precise and give the right answer. With these 2 pivotal abilities, we can see that we almost entered the area of large language models, and currently many large companies like Google, Anthropic, OpenAI, Baidu have all have their own large language models. And even some institutions like university and other organizations also developed their own large language models. So even large language models is so powerful, but it also have many questions that make it hard to be widely used. For example, the first problem of it is it can generate toxic language, which include hate speech or abuse, or some dangerous expressions, such as it includes bombs. The second problem of it is its hallucination. Because we are researchers, I think we will have the experience that if we input some academic for example, we want the ChatGPT look for an academic papers for us. If we don't give it enough instructions, it is possible for it to generate content that is not real or made up by itself. And the third problem of it is its fairness. Because the training data of large language models are mainly collected online, so this data can hardly be examined totally. So it's possible that these data are biased according to gender, age, or race, etc. So to solve these problems, we have to understand how a large language model works and what it learned inside. And the explainability techniques is a way for us to understand it. Next, I'm going to talk about the explainability techniques for traditional fine-tuning paradigm, which also are the techniques that are mainly used for prompting-based paradigms. And here I will divide these techniques into 2 categories. The first one is local explanation, and the second one is global explanation. For local explanation, it mainly tries to explain why a specific prediction is made, and how this prediction can be made in this way from the for example, from the feature perspective, or from the parameter perspective, or like the third category, it uses some synthetic examples to explain it. And for global explanation, it is mainly to explain this model from the level of model components, such as neurons or hidden layers. Okay, first I will introduce the local explanation, and the first perspective is from the feature level. From the feature perspective, there are several methods that are usually used in feature attribution. Actually, these methods are also applied in attention-based explanation. The first method is perturbation-based explanation. It's a bottom-up method, and this kind and the representative method in this category is leave one out. Actually, the idea is pretty simple. For example, we give a model a sentence, and we in the classification task we make it to classify whether this sentence is positive or negative. The simplest method is that we can take one word in this context out, and we can see how the output changes. Just like the example here, we give the this is a question answering task. We give the model a context, and then we ask a question. In this context, it said that in 1899, John has invested some money for Tesla. But Tesla used this money to fund its another experiment. And the question is that, what did Tesla spend this money on? The original answer to this, of course, is the Colorado Springs experiments. Then we can omit this word in the original question. Here we omit did. Actually, did is means that we are asking about the question in the in 1899. So when we omit this word, this question just becomes what happens right now. Actually, it's nothing to do with the context already. But when we omit this word, the prediction, the model prediction is still the same, and even with higher confidence score. So this is a good way that to show that this model doesn't learn very well, and it didn't, and it can't identify the importance of it, or see even learn in the opposite way. And the second mainstream method in feature attribution is gradient based. Actually, a lot of papers are based on this kind of method, and here I will only introduce the rule gradient. It is mainly to see the output changes according to the input changes. Here we can see from this graph, when textual input are turned into embeddings and sent into these language models, these language models can make predictions in a set of date, and in this date there are many words. Each word will get a logits, and these logits will send to a normalization, then it will output the probability. Actually, from here we use these logits to calculate the gradient and back propagate it to the input to see each part of the input, how large is the gradient. The value of the gradient is larger, and then the importance of the inputs will increase. And a third method is the surrogate model. Actually, this method is pretty intuitive for us humans, and it's more understandable. The basic the model here I'm introducing is LLM, and the basic idea is to approximate a prediction or see a data point in a local areas. It will sample the data points around the explained data, and use this sampled data point to approximate a linear classifier to explain this model. Usually, in computer vision, we all know that there are many pixels and there are so many dimensions of the features. So usually they will turn these pixels into super pixels. For example, they will use or turning 20 multiply 20 window to turn that small area of pixels into a super pixels to just to reduce the explained dimensions. And in natural language processing, they might be change the length of the tokens to explain the input. And the learning object of this method is pretty simple too. We can see from this equation that the omega g is to try to control the explained complexity. Let's see, it try to reduce the explained input feature dimensions, and then this pi x here is try to use the data point close to the explained data point, make this sample data point as close to the explained data point as possible. And another objective of it is try to make the approximated classifier, the result of it to as similar to the original non-annihilator classifiers as possible. So this is a very good explanation method, because it can give people very intuitive explanation, and it is not that hard to understand. So many applications has happened in this area. And that's all for the feature attribution method. Next, I will explain. I will introduce the attention-based method. Actually, there is no large difference in these two areas. The biggest difference, I think, is that for feature attribution, it tries to explain the importance of features, but for attention-based, it is try to learn some patterns and also importance in parameters, that is attentions. And the first method is visualization. I'm going to introduce because we don't have this method in feature attribution method, so I will just mention this. Here we can see that it's very simple, because in self-attention we have in self-attention, for example, with one sentence we have each word, and this word will have its attention around with other words in that context. Here we can see this is a two-sentence input to a model. The CLS means that at the beginning of the sentence, and then it follows a small sentence, the rabbit quickly hopped. And the sep means that the separation of two sentences. Then it follows another sentences and the sep. So here it means two sentences, and the right part is the same sentence, just to make these two columns so that we can draw lines. Here we can see that the density of the line means that the attention weights. So the line more dense the lines, the higher the attention weights is. From here we can see that attention weights are very high when it is in the same sentences. So that means the language models are usually focused more on information in one sentences. And here we can see this line rabbits with the hopped are pretty thin. So that means the language models think that rabbit and hopped are usually connected. And for heat maps, it's actually another form of this, another form of visualization of the same information. So I'm now going to talk more about this. And here I'm what I want to see is actually, as I mentioned, the attention-based method are quite similar with the feature attributions. Here is one example. The left part is a trained model, and after trained we can get an attention distribution, and then we frozen this model. We can try to zero out some weights here, and then we let the model to predict again. Then we can calculate the changes between these two predictions and try to find out the importance of attention weights. Actually, there are a huge debate about whether attention can be used as an object to interpret the importance of to interpret the learned knowledge, because as we know, input features can directly represent these inputs, but for attentions, it is not that directly related to inputs. It is basically a form to represent the correlation between these inputs. And there is a survey to introduce these debates, but in general, we still take attention as an important indicator because it actually learns some patterns in it. Okay, the third class of the local explanation is example-based explanation. Actually, this kind of explanation is very useful for the closed source models. For example, in the left part is the adversarial examples. It's very simple. It's just to use the models to manipulate the sentences. Here we can see in this sentence it will substitute some words, and after changing the words, actually the meaning of the sentences don't change much for our humans, but for models, the prediction will totally turn around. So this is a problem adopted from the adversarial attack. It can expose the weakness of the models. And another method in the right part is the counterfactual examples. It's a little bit different from adversarial examples. In counterfactual examples, it's just to try to manipulate the original sentences, and for example, it will delete some parts which is quite similar to the observation-based ones, and it can also turn these sentences into the opposite meaning, and or say it will change some words in it. Then it after changing, we know that it's a correct prediction, and we can see whether the model can predict in a correct way. So we can test it how the model performance. And this is also a very good technique for data augmentation. Okay, that's all the methods for the local explanation. Next, I will introduce the global explanation. The first technique is the problem-based techniques. It's pretty simple. Actually, it's when we train the model, we can get the representation of these inputs, and then we will use a supervised classifier. This classifier can are usually targeted for a specific kind of knowledge. For example, it can be a grammatical knowledge. Here we can see it can be a classifier that probe whether this input is for a verb. So here we can see that with this kind of probing classifiers, we can know what knowledge a model has learned in the level of its neurons or in the level of its layers. In this example, we can see below this in the below actually this is a TSNE graph, which in this kind of graph, the closed the same class will be clustered closely, and for different class they will be far away. And in the right part, we can see actually this cluster, each cluster represent a different kind of grammatical components. For example, for the VP, it means that verb phrases. For ADGP, it means adjective phrases. So we can see here that for the layer 1 and the layer 2, it can be clustered very well. And so that means that for language models, especially for BERT models like BERT and above, their first few layers are mainly learning the syntactic or grammatic knowledge. But as we know, BERT has 12 layers, and the layer 11 and the layer 12 are the last 2 layers of it, and it can hardly distinguish this grammatical knowledge. So that means these 2 layers are mainly targeted at semantic knowledge. And another techniques is to try to find the neuron activation. And the traditional method we use are also problem-based, but here this is a new technique, but it's very rough, that are published by OpenAI recently. They are trying to explain GPT-2 with GPT-4. The process is pretty simple. First, they will give this GPT-4 the related text sequences and its neuron activations. These 2 will be given to GPT-4 and let it to make explanation to this neuron. For example, it will see that this neuron is references to movies, characters, and entertainment. And then with its explanations, it used the reverse engineering techniques to translate this explanation to the relevant text. Then they will compare the original relevant text with the predicted relevant text from the reverse engineering, and compute these similarities to see if this neuron explanation is valid. Actually, this is a very good technique, because in traditional neuron activation works, we can only try to look into a few neurons, because for each neuron we need a classifier to make predictions. We cannot look into every neurons because there are too many. So there are always some ranking techniques to select a few important neurons and then trying to explain them. But with this kind of techniques, we are able to explain all these neurons, and I think with all this neuron explanation, maybe we can find some patterns or other important things. But the problem of this method is OpenAI didn't disclose many details about how they do this and what the reverse engineering technique is, and the evaluation metrics of this is very rough too. So we can wait in the future, see if we can make this method more robust. Okay. The last section is all the interpretability techniques we use. We use basically, and next I'm going to introduce some explanation for the prompting-based paradigms. Actually, in these paradigms, because it happens very recently, so there are a few works to explain it. And today I'm going to introduce the some explanations for the two pivotal abilities that I mentioned before. So the first I'm going to introduce is the future learning. In our area, sometimes it is also called in context learning. And here they want to know for prompting based paradigm, when they are making predictions or what they are count on. Whether they are count on the semantic priori, that means the knowledge that model learned from the trained data, or whether they truly have the very strong reasoning ability. So from this example, we can see the left part is the regular in-context learning, and they gave the model a few examples. For example, in the left part, the contain no weight, that this is a negative expression, and the very good viewing is a positive expression. And then they give the model another expression, smile on your face. Of course, this is a positive one. And in the second experiment, they try to flip the labels that they gave in the examples. They make the no weight positive and goodwilling as the negative. Then they ask the model to predict smile. And this model gave the negative, gave the answer negative. So here, we can see that large language models depend, unlike traditional language models, large language models is able to learn the new correlations in these examples. So they depend less on semantic priori. But whether they have the very strong reasoning ability, like if we change these labels to unrelated ones, whether they can still learn. If they can still learn, that means they are able to learn the input label mappings, and that's a very strong reasoning ability. So in the third experiment, they try to change the label to the unrelated words, like they change the negative to for and change positive to bar, and make the model to predict again. And this model is still able to learn these new labels. So the general conclusion we can get here is that large language models are able to learn the input label mappings, and they really have very strong reasoning abilities. But for small models like bird level, they still rely heavily on the semantic priori. That means for model like bird, if we give such kind of input, they maybe still give you that a smile on your face is positive. And the second most recent research about the prompting based works is how this chain of thought prompting affects the large language models. Here we can see that the circle means that the original prompt, which include the task description, examples, and the questions. And the diamond means that the prompt that are rewarded. And here these saliency scores are means that whether the output is sensitive to this prompt. So we'd like this sensitive score as low as possible. And we can see that for the standard prompting, the skew is much larger than the COT prompting. here they use 4 different metrics to try to measure this, and they find that for large language models, they are kind of sensitive to the how these prompts are phrased. So when we are trying to ask a large language model to make input, we better to use the COT prompting instead of use the random standard prompting, because for standard prompting, we usually get a very inconsistent output, and sometimes it even perform very badly. And we have been talked about the capabilities of large language models. Then there are also 2 important problems in large language models. The first one is its hallucination. As we said, that means the model usually generates text that is incorrect or not in real. And the remedies for this are we can use clean data, but this is very difficult because for large language models, the data is too large. We can really to look into all these data. And the second solution is to restrain this model generation. But this is this means we need to add more functions into this model. It's maybe it's possible in the future. And the third solution, we use better prompts. This is more practical one for us right now. And the second question of large language models is its uncertainty. That means when we give it even the same prompt, it might output different generation each time. So we need to develop some metrics to measure this uncertainty and try to find some measures to decrease the uncertainty as much as possible. Okay. Lastly, I'd like to introduce some future research directions. The first one is that currently we lack ground truth explanation. Even I have introduced so many explainability techniques, but we can see one of them is definitely the ground truth explanation. So we don't know which one is ground truth explanation, and the general method that we use to try to find a good explanation, we can use several different explanations to try to find the overlapped ones. And also it's very hard for us to give ground truth explanations, because if we give the model that these explanations from us human, it might be just our understanding of this problem. It's not the understanding of the models. So this is a very significant question here right now. And the second part is that we still don't know how the emergent abilities, that means that 2 important abilities that this model gets. For example, we don't know what kind of model structures can definitely generate this kind of abilities, and what is the smallest model skill that can generate this kind of abilities. And we also don't know whether these kind of abilities are because of data, for example, data contamination. And we also don't know that the data quality and the balance, the trade-off of data quality and the data quantity on this kind of problem. And the third is that currently we don't know the difference between 2 paradigms. We know that they have different performance on out of distribution data, but we don't know why, and we don't know their reasoning we don't know their reasoning schemes towards two paradigms for in distribution data. They all perform good in distribution data, but whether they rely on the same reasoning schemes. And we also need to look into why large language models is better at out of distribution reasoning. And the first point is that actually large language models also have shortcut learning problems. There is a research that shows that large language models may be more sensitive to the text in the tail, in the beginning part of the input text, and they focus less on the middle and the tail. So we need to develop some methods to try to solve this kind of problem. And the fifth point is kind of interesting. And recently there is a research team that proposing that our explanation are mainly made on post hoc sightings. We should focus also. We should also. That means we are trying to explain the fully trained models instead of focus more on the different checkpoints in the training process. So we cannot know how this training process evolve, and we met and that may be the reason that we don't know how this emergent ability happen, and we also don't know if in this training process there are something that disappear gradually, but which are very important. And the sixth part is the attention redundancy. As I said in the attention-based explanation, there are perturbation-based techniques try to mask out some attention weights, and the research shows that when we mask out some part of the attention weights, the model performance doesn't change. That means these attentions may be redundant. So this is a good way for us to develop model compression algorithms in the future. And the last is the safety and ethics. For this part, I think still we need more regularization techniques to implement our hopes for these large language models. Okay, that's all. Thank you for listening.
Thank you, Haiyan, for a very interesting and detailed talk. Yeah. So now let's enter the question and answer session. If anyone have any question to discuss, please feel free to unmute yourself, or you can leave your comments or thoughts in the chat.
Okay, Haiyan, can you hear me?
Hi, yeah, I can hear you.
Very interesting talk, thank you. I assume this talk is based on a survey from you, right?
Yes. Yes, this is based on the survey that we finished this summer.
Okay, thank you. And I'm interested in the part you mentioned, the hallucination and the unstable prediction of large language models. Actually, we also observed some of these unstable predictions in our recent experiments. And we found that in-context learning from few-shot examples can largely alleviate these problems. For example, if we use in-context learning, we can largely reduce the variance of the prediction results. So I was wondering, during your survey, did you find any similar results from other papers?
Yes, I think in context learning definitely can animate your output, and but the question is what kind of other research that you are trying to asking that
Yeah, I'm just interested if these are like this similar
okay. I
findings
mean,
from.
are you asking is there any other method that can animate the hallucination?
Yeah, I'm not talking about the hallucination. I'm talking about the unstable prediction problem, the second one you mentioned.
Okay.
Yeah.
Yeah. Oh, okay. As there is research mentioned in my PPT that actually in context learning is one way that you can solve it. But if you want to get the inconsistent you want to get the consistent output, you need to give it more detailed prompts, like
More
chain of
detailed prompts, right?
yes, like chain of thought prompts. You better, for example, if you want to inference in a specific pattern, you better to give that kind of pattern, like explanation or see our thought process to it.
Okay.
Yeah, then it will learn that pattern and try to inference it that way.
Okay.
That's the method that we know so far.
Okay, thank you. And another question is about the future work you mentioned. You mentioned this attention redundancy.
Yes.
Could you please explain a little bit more about that?
For attention redundancy, that is when we are trying to look into what knowledge this attention has embedded. There might be a few there might be many attention has that embed the same knowledge. So when we try to mask out some of it, if the prediction or see the output of this model doesn't change, then we can maybe considering pruning it.
Okay. Okay.
Yes,
Thank you.
that's a way. Yeah, I think that's a way for us to do pruning.
Yeah. When you mean model compression, you mean like pruning the model, right?
Yes.
Okay. Thank you.
Thank you.
Okay, Haiyan, we have a question in the chat, so I will read it out for you.
Yeah.
Jeff Gao is asking, can you please elaborate why multiple outputs are generated from the same prompts in one model?
I think it's because when we send the same prompt into these models, they might originally they have different output that maybe have the similar scores. They just output one randomly. So so we can't see there is a fixed the best answer to this. So that's possible, especially when we give it the prompts that are not very detailed. Then we can get this we can get many kinds of the outputs. So there may be these outputs are with the similar scores, but if we give it very detailed instructions, it will know how to do this process, and they will have less options for the output. So we can usually get a very consistent output.
Thank you. Yeah, I hope that's clear enough. Yes, thank you very much. We still have a few more minutes. Any more questions for Haiyan?
Yeah, Haiyan, I have a question. How many tokens will be filled if using attention map?
That depends. That really depends, because actually this attention map depends on the length of your inputs, and that also depends on what kind of model you you are trying to use. So but usually we don't use that kind of method because you cannot draw. For example, you have a paragraph that, or see you have a documentation, you have really too many input tokens, so it's very hard to display in this kind of graph.
Oh,
But if you
okay.
are looking into just a small sentence or just a small paragraph with hundreds of words, then that kind of visualization would be very good for us human to examine.
Okay. Okay. Thanks.
Yeah. Thank you.
Yeah. I saw Yu Chuang previously unmute himself. Yeah. Do you have any question to ask?
Yeah, I have some question about recently I tried to do some work on robots, emotion recognition with a playable way for human-robot interaction. I always think about how to make the explanation for robots perception, for example, emotion recognition in human preferred. I mean, how do you think? Are there some tips for it? Because for human level, because sometimes when we say it's explainable, but sometimes human maybe do not need the explanation for it. Do you have some thoughts on these kind of things from the survey? You have so many net tag. Yeah.
May I ask what kind of the detailed task in your research?
For me, mostly I do the emotion recognition in human-robot interaction. Robot need to know human emotion, but sometimes with language, only with language, sometimes with multi-modal language and weighing. So, but different from other emotion recognition in other normal agent, we will consider human from a human first. And maybe you give so many explanation, but the person do not need it. It's a problem how to think and from a tech view. Yeah.
I see. May I ask, when you try to make this emotion prediction, that do you use image or you can use image, language, and various combination of it, right?
Yeah, both are
unique. I think for the if you are using both image and language, I think maybe you can use explanation techniques to see if there are some overlaps of it.
Cool. Yeah.
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 Or and if there are any correlations that can help each other to make predictions, I guess.
Okay, to find attention or like the kind of things, and also.
Yeah, attention is one way, or you can also look into the features.
And also another things, maybe it's a kind of, I see you have the concept-based explanation.
Yes, I know that.
Yeah, so the concept, when you say concept, it's a kind of like abstract concept. Or that the large language model has some specific concept system or language system, maybe human cannot understand like these kind of things. And do you consider this in your survey? Like maybe they use okay.
Yes, sure. I understand your question. I think the biggest problem of concept is that when we trying to use a concept, that must be a concept that we human understand. Yeah, that's a problem. Yeah, we need to train this concept with the data that we understand, and we don't know whether this concept is well trained. We can only give it some examples. We can only use some we see some perspective of information of this concept. So I think it's very limited, although it is very intuitive for us.
Okay, cool.
And for this kind of concept that model understand, but we human don't understand, this is a big problem.
Yeah. Do you consider neurosymbolic AI kind of the explanation for the large language model, because the language is a kind of the new, it's a symbolic things like that, like from a kind of reasoning from this concept to another, it's a kind of neural AI things, neural symbolic AI things.
Actually, currently we have a work that's trying to focus on the neuron, but we are mainly looking into this concept, just like you said, this concept that we cannot understand whether this neuron learn a specific concept. So we haven't looked into the symbolic topic.
Okay.
But maybe it is important.
Okay, cool. Yeah, thank you.
Yeah.
Thank you. It's clear.
Thank
yeah,
you.
That's all
thank
my
you for your
question.
questions.
Yeah, thank you for the questions. I'm keeping an eye on the time, and how fast it flies. So I think we can wrap up today's session and give Haiyan Zhao another round of applause if you can hear me.
Okay, thank you.
So before we end up the session, let me share my screen again.
Okay.
Yeah, okay. There are some other questions. There is a last question. If you don't have time, I prefer the free-zone movement. If I'm pronouncing in right way, you can join the Slack and maybe Haiyan, if you like, you can join the Slack. We can talk for future and yeah.
Yeah.
Okay. Thank you. Please invite me to there.
Yeah. I put the link there.
Okay.
Guan, you can continue. Yeah.
Yes. So the recording and the slides of today's talk will be shared in our WeChat group, which you can search by the name MLLM 研讨会交流群. You can also scan the QR code to visit the MLLM website to follow us for the upcoming talks. So in November, it's gonna be a quite busy month with 4 talks coming. 1 talk each week. So please follow the website to get the most updated information. So we look forward to seeing you maybe next Saturday in another talk. So let's thank our speaker again. And I wish you all have a very nice autumn weekend. Keep warm and relax.
Yeah, cool.